Welcome back, students. In this video segment, we will cover two sections. Section 7.4, Convolution Integrals, and 7.5, Systems of Linear Differential Equations. So let's start with section 7.4, Convolution Integrals. Both of these sections, 7.4 and 7.5, by the way, are extremely important sections for STEM majors, for people going into specifically physics and then ultimately into engineering, or just sticking with physics. So let's get started. I'll start with a couple of true or false questions. So true or false, the inverse Laplace transform of, let's say, f of s plus another g of capital G of s equals the inverse Laplace transform of f of s plus the inverse Laplace transform of g of s. And without hesitation, you should say, you're right, unless you said false. Yes, it's true. Okay, so we've been using this to solve differential equations over and over and over and over again. So let's say that's part A. So part B, the inverse Laplace transform of f of s times g of s, the product of two functions of s, equals the inverse Laplace transform of f of s times the inverse Laplace transform of g of s. And I'd like you to think about that. I'm going to give you a hint. Your hint is that it's not true. It's absolutely false. I wish it were true. If this were true, a lot of our work with Laplace transforms would be unnecessary, or our work would be vastly reduced. This is a great big false. Great big false. Okay, it's not just false, it's a great big false. Okay, so the section 7.4 really answers the question, how do we deal with the inverse Laplace transform of products? And the short unsophisticated answer would be, we deal with it the way we've done this so far, which is a lot of work. This section addresses a systematic way of dealing with the inverse Laplace transform of the product. So in order to do this, we have to invent right now a new kind of product, a new kind of multiplication, if you will. I don't want to call it multiplication because it's not really multiplication. Have we ever had to invent other multiplications? Of course. When we studied vector spaces early on in the semester, multiplication is a scalar multiplication could be defined in quite a broad range of ways. Okay, so we're going to define a new kind of quote-unquote multiplication. So let's define what we're going to call the convolution product. So the definition of this thing we're going to call a convolution product, or simply just a convolution. Okay, I'm saying product because the definition and the big result that's coming up in about 10 minutes or so helps us find the answer to the red question above, inverse Laplace transform of fg, of the product of f and g with some other kind of product, namely the convolution. So if that didn't make sense, I really didn't reveal too much. So let's define that convolution product. Okay, let me get rid of some of my scratch here. Okay, so the definition of the convolution product is this. if we have two functions of t, the definition of f of t star is going to be the operation for this convolution product. F of t star g of t is the integral, and we have to be real careful with the symbols here, because the symbols, there are a couple of symbols that look similar. It's the integral from 0 to t of the first function f evaluated at the Greek letter tau. This is not a t, this is a tau, same tau that's used often in physics to represent torque. F of tau times, this is regular multiplication on the integral sign, g of t minus tau, and the integration is taking place with respect to tau. Okay. Personally, I don't like this use of the variable tau because it looks so much like the variable t, but it's pretty standard. I've noticed it in most textbooks that we could have used the letter, say, u instead of tau, but no, it's really kind of common. So we'll stick with the common use of the variable tau. Okay. So for example, find, let's say, f star g if f of t equals cosine of t and g of t equals just plain old t. Okay. So f of t star, or and this is common terminology. F of t convolved. I know it sounds really funny. F of g convolved. I've heard a lot of people say convoluted with, but convolved with g. That's the kind of standard terminology in the math community. F of t convolved with g of t means cosine of t star, or convolved with t. And now let's use the definition of the convolution. The definition of the convolution of cosine with t is the integral from 0 to t of f, the first function, f of tau, so cosine of tau, times g evaluated at t minus tau, so times t minus tau. Integration is taking place with respect to tau. Okay. Now, this integral is a standard integral we would see in Calc 2. The technique of integration we'll use is just the same technique we would use in Calc 2, is integration by parts. So I'm going to integrate by parts, since I'm going to indicate that red, so by parts. Off to the side here, I'm going to let u equal t minus tau dv equal cosine of tau. For those of you who'd like to use the tabular integration form of this is just fine too. So by parts, u equals t minus tau, dv equals cosine of tau d tau. Be careful here, because it looks like we have two variables in this integral, but really the integration is done with respect to tau, so tau is the live variable now. T is held fixed. So with that in mind, du, the derivative of t is 0, because t is being held fixed, and the derivative of negative tau is negative 1, so this is negative d tau. And v, the integral of cosine, is sine, so the sine of not t, but tau. Okay, so now let's use the integration by parts formula. Integration by parts formula says this integral is u times v, so t minus tau times the sine of tau. It's a definite integral, so this is for tau varying between 0 and t. remember these variables, we have to be careful with them because they're so similar looking. Minus the integral of v du. Well, du is already negative, so it's really plus the integral of sine of tau times 1. So sine of tau times 1 d tau. And this is also as tau varies from 0 to t. Okay, so let's continue with this. I'm not going to substitute the limits of integration in the first term here. I'm going to wait until I integrate the sine of tau first. So this is t minus tau, no change, sine of tau, and the integral of sine is negative cosine of tau, and this entire expression is carried between, I almost did it there, I have a little t I just wrote. This entire expression is carried as tau varies between 0 and t. And remember this, the problem with the t's and the tau's, believe it or not, when I took this stuff, oh God, let's say many decades ago, I remember sitting in the library frustrated with not being able to get the right answer because I would confuse t's and tau's. It's so easy to do that. Anyhow, so substituting the upper limit of integration for tau equals t, I get 0 for the first term, 0 for substituting tau equals t into t minus tau sine tau. So I get 0 minus substituting tau equals t into the cosine, I get cosine of t. So there's the value of this expression at the upper limit, minus the value of the expression at the lower limit, tau equals 0. Well, if tau equals 0, and I'm going to put a little green arrow here, if tau equals 0 right there into the sine of tau, I'm going to get 0. Okay, so I'm going to get 0, well, now I'm substituting tau equals 0, so 0 minus the cosine of 0, which is 1. Okay, so let me get rid of my little green arrow there. So the result is 1 minus cosine t. So the net result is that the cosine of t star, or convolved with t, is 1 minus cosine t. Right now, this result probably has very little meaning to you, other than it's just some bizarre integral of the product of two functions. So now we get to the core of this section, the reason for this section. This convolution is going to allow us to go back to the red question, which I'm kind of underlining partially in green here, and answer the question, how do we deal with the inverse Laplace transform of just the regular product of two functions of s? Now I'm gonna derive the result, and I'm not going to ask you to derive it on your final exam or on your test for spring 2020. However, I am going to derive it. It's a derivation that if you're a math major, you probably get a little kick out of it. If you're not a math major, at the end of the result, I will write in big letters, big result, and you can fast forward through the video if you'd like, and until you see the words big result if you're not interested in watching the derivation. Okay, so here goes. I want a result for, I want to take the Laplace transform of the convolution. So here's our beginning here. So suppose we have, so let's let the Laplace transform of small f of t be big F of s, and let's let the Laplace transform of small g of t be big G of s, just as our standard for this problem. All right. Okay, so let's find an expression for the Laplace transform of f of t convolved with or star g of t, f of t convoluted with or convolved with g of t. Now we're going to go all the way back to the definition of the Laplace transform. Okay, so we're going to take first of all, we're going to go into the definition of the convolution. The definition of the convolution, remember, is the integral from 0 to t f of tau g of t minus tau integration with respect to tau. Okay, now what is the definition of the Laplace transform? You might have forgotten that. Just off to the side here, the definition of the Laplace transform of f of t is the integral from 0 to infinity of e to the minus st times f of t dt. So we're going to use that definition right now to get our next line. Okay, so this equals the integral from 0 to infinity of e to the minus st, Laplace transform starts with e to the minus st, times that bizarre convolution integral. 0 t f of tau, tau again looks like a t. I have to be so careful with that. So f of tau g of t minus tau d tau. Okay, I'm going to slip that e to the minus st into the last integral on the right. I'm going to slip that inside. The reason I can do that is that the integration of the, oops, I forgot the dt for the Laplace transform. The reason why I can pass the e to the minus st inside the integral from 0 to t is that the integral from 0 to t is done with respect to tau, not t. So e to the minus st is constant with respect to integration with respect to tau. Okay, so now I'm going to do that. I am going to, simple steps, 0 to infinity, integral 0 to t, e to the negative st, f of tau, g of t minus tau, d tau, and then after that with respect to t. And this looks like exactly what you're thinking it is. It is an iterated integral. It is an iterated integral that's a result of finding the double integral of the quantity e to the minus st f of tau g of t minus tau d tau d tau dt or whatever. Okay, so what I'd like to do, and this happens so commonly when we get these doubly iterated integrals in science-based math, that if we reverse the order of integration, things tend to pop out really nicely. Now, we can't simply reverse the order of integration and then reverse the limits of integration, because the limits of integration are not constant. Okay, so what I'm going to do is, off to the side here, I'm going to graph the region of integration, and then we'll deal with, oops, I'm going to graph the region of integration as soon as I can get a graph showing up. I'm going to graph the region of integration. And then we're going to use that region, the graph to the region, to switch our limits. Okay, so the axes are not y and x. The axes are tau, vertical, and t, horizontal. Okay. Now the innermost limits in this doubly iterated integral have tau varying from 0 to t. So the curve t equals tau is just like having y equals x if this were in the xy plane. So this is t for y equals tau for x. So tau in the first integration is varying, with a green line to integrate the direction in which we're integrating. Tau is varying from tau equals 0. Tau equals 0 is the t-axis to tau equals t. And then t goes from 0 to infinity. So after we integrate from the t-axis up to the line t equals tau, we integrate from 0 to infinity along the t-axis. So that's what that's happened. What that's saying is, you can kind of think about it as we're integrating throughout this little rectangle here. I want to get rid of that little green line inside there. If I can do it without messing my drawing up too much. There we go. What this is saying is that we're integrating inside this triangle in the first quadrant, but then we're letting the little dotted vertical side of the triangle go to infinity. Again, tau goes from, in the innermost integral, tau goes from 0 to t. So tau varies between tau equals 0 and the function tau equals t. And then t integrates from 0 to, say, the dotted line, and then we let the dotted line go off to infinity, if you will. So you can think about it as we're integrating over this infinitely big triangle as the little dotted line shoots off to infinity. Okay. So let's reverse the order of integration. If we reverse the order of integration, we're still integrating e to the negative st f of tau, g of t minus tau, d tau, dt rather, and then d tau. Then the innermost integration tells us that we're integrating between the functions t equals tau, and I'm going to put a little green arrow in here to indicate the direction of our integration. The innermost limits, the innermost integral has t varying from tau, and I'm putting a little circle around that right here. This is t equals tau to where? To the little dotted vertical line, which is being pushed off to infinity. Don't know why I have to do that in green. So, take that out of there. I know, I'm being picky. Okay. So tau, t goes from t equals tau to t equals infinity. We're pulling that little vertical line off to infinity. And finally, what are the limits on tau? If I let that little vertical line shoot off to infinity, I get a huge triangle, a huge triangle, and the limits on tau of that triangle are 0 to infinity. Okay, so when we do that, effectively we've done this. We've integrated over this region, just in case you're not quite sure. We've integrated over this entire shaded region here, and it goes on to infinity. So here, let's just indicate this to indicate that this shoots off to infinity. Okay. Well, let's keep going with this. By the way, this could have, for you mathematicians, this could have been made much more rigorous if we actually, before we put all those infinities in there, we actually just integrated over a finite triangle, with the vertical line being actually placed at t equals a, and then let's just let t go to infinity. So we could have been much more formal about this. Okay, in any case, moving forward, let's take a look at that really weird looking function we're integrating, e to the negative st, f of tau, g of t minus tau, dt first, dt. Is there anything that can be factored out of that first integral dt? And the answer is yes. The f of tau in the first integral is constant with respect to the integration with respect to t, is constant with respect to t. So I'm factoring that out. Okay. Believe it or not, we're almost there with this. I know for the non-mathematician types, this is probably a little grueling because you have to think way back with double integrals and iterated integrals and such, but that's good. That's good for you. Okay. Onward. Now, that inner integral from tau to infinity of e to the minus st g of t minus tau, that looks almost like a Laplace transform. Almost. There's some problems. The limits don't go from 0 to infinity, and the function we're integrating is e to the minus st, which is really good, but it's not times g of t, it's g of t minus tau. So I'm going to make a u substitution in that innermost integral. In the innermost integral, I'm going to let u equal t minus tau. Okay. Now then du, you have to be careful. What's variable now? The variable is t. We're integrating with respect to t. So du is just 1 dt. Okay, and I'm going to make that substitution into the innermost integral, So I'm integrating from 0 to infinity of f of tau. When I substitute put the u substitution into the limits of integration, or if I put the limits of integration into the u substitution, what's going to happen? Well, let's do it. The lower limit of integration occurs when t equals tau. When t equals tau in the red substitution, u equals 0. So what about if t equals infinity? What happens to t minus tau? Tau is held fixed in this integral. T minus tau as t goes to infinity. What's infinity minus a constant tau? It's still infinite. Okay. So then we get e to the minus s, well, no longer t. Well, if u equals t minus tau, then t equals u plus tau. Okay. All I did is I solved u equals t minus tau for t. Okay. So then this is kind of nice. G of u and dt is du, excuse me, and then with respect to tau. So that innermost integral still looks a lot like a Laplace transform, except now we have another little problem. The problem is that, well, the e to the minus s is great. It needs to be e to the minus su if we're to produce a Laplace transform. So let's fix that. Let's deal with that. Well, the e to the minus s times u plus tau, what I can do with that negative s is distributed inside. So this becomes e to the minus su minus s tau. Okay? So I'm going to use a little bit of pre-calc that says then that e to the minus su minus s tau is e to the minus s tau times e to the minus su, and yes, I know I took it outside of the integral sign, g of u du d tau, u goes from 0 to infinity. How did I get that e to the minus s tau out of there, out of the integral? The integral is with respect to u. E to the minus s tau doesn't have a u in it. Is not a function of u. It's a constant with respect to u. Okay. Now that innermost integral, that little guy is a Laplace transform. That little inner integral is a Laplace transform. Not only that, the last integral is done with respect to tau. The innermost integral has no tau in it, so it's constant. So I can rewrite this as the integral from 0 to infinity. I'm going to write the e to the minus s tau first. F of tau d tau. And factor out that innermost integral. The innermost integral is not a function of tau, so it's constant with respect to tau. 0 to infinity, e to the minus su g of u du. And for you non-math majors, here's your relief. Here's your relief. this is the big result. Big result. Okay, and that says, well, what's the first expression? The e to the minus s tau, f of tau, d tau from 0 to infinity. That's just the Laplace transform of f of t. What's the second one? The second expression, the second integral, 0 to infinity, e to the minus st, su, g of u du, that's the Laplace transform of g of t with respect to t. The variables of integration have no effect on what the expression is equal to. Okay, so the first integral is a Laplace transform, whether we're integrating with respect to t, tau, u, v, alpha, beta, anything. As long as the structure is e to the minus s variable, f of variable, d variable, from 0 to infinity, that is a Laplace transform. So let me consolidate the net result here of this derivation. I was looking at, to begin with, the Laplace transform of f star g. So the big result is the Laplace transform of f of t convolved with, or star, or convoluted with, if you want to use that language, is the Laplace transform of f of t times, regular times, the Laplace transform of g of t. This is as close as we can get to distributing the Laplace transform into products, into multiplication. The bottom line is it doesn't, but it does distribute into the convolution. Another way to view this would be that the Laplace transform of f of t star g of t is the Laplace transform of the first function times the Laplace transform of the second function using f of s and g of s. Okay, this is extremely important. This formula holds together this whole section, and for the rest of the section, I'm going to illustrate just how this formula makes a lot of stuff possible. Okay. Alrighty then. So how does this address the original question? The original question is, what about the inverse Laplace transform of f of s times g of s? Well, it's right in front of us. Not in the form that maybe we would like to see it, but it's right in front of us. It says that the inverse Laplace transform of f of s times g of s is f of t star g of t. Or we can write it as the inverse Laplace transform of f of s times, and this is regular multiplication, times g of s, is the inverse Laplace transform of capital F of s, that's small f of t, convolved with the inverse Laplace transform of capital G of s. This is how we deal with the inverse Laplace transform of the product of two functions of s. The inverse Laplace transform does not distribute inside precisely, but it sort of does. But the product that occurs after you've distributed it is not a regular product, it's a convolution. So now let's use this in a simple example before we get to more elaborate examples here. So, example: find the inverse Laplace transform of the product of two functions of s. 1 over s minus 2, s plus 1. So why is that the inverse Laplace transform of the product of two functions of s? It looks like just one function of s. Well, not really. It is in the sense that it's one rational expression, but it can be broken down into 1 over s minus 2 times 1 over s plus 1. Now, we've dealt with this kind of inverse Laplace transform bunches of times, especially if you're caught up with, or if you've done a lot of the homework. We use partial fractions. That's one way of doing this. That's one way of doing this, okay? But we could also use this convolution theorem, this big result, to do this. The f of s, the capital F of s is 1 over s minus 2. The capital G of s is 1 over s plus 1. And the big result says that this equals the inverse Laplace transform of 1 convolved with the inverse Laplace transform of the other. Okay, these individual inverse Laplace transforms are trivial. What's the inverse Laplace transform of 1 over s minus 2? What's the inverse Laplace transform of 1 over s minus 2? What should it involve? The exponential function, e to the 2t, convolved with the inverse Laplace transform of 1 over s plus 1 is e to the minus t. Okay, now this is not a normal product. This is where we have to do some work, or some serious work. This is a convolution. So remember what the convolution says, just off to the left here. F convolved with g is the integral from 0 to t f of tau g of t minus tau d tau. We can't escape our definition of the convolution. Okay, so let's use that definition on our product, on our convolution product here. So this is the integral from 0 to t, e to the 2 t minus tau. Oh, that's not right. It's f of tau, not f of t minus tau. Sorry about that. Let me clean that up. F of tau is e to the 2 tau times g of t minus tau, e to the minus t minus tau d tau. This integral is not too rough. The toughest part about it is that we got to keep track of t's and tau's. They're not the same variable. So let's do this. This becomes the integral from 0 to t, e to the 2 tau, e to the minus t, e to the positive tau d tau. Okay, now the integration is occurring with respect to tau, so e to the minus t in the middle there of that product is constant, can be factored out of the integral. The e to the 2 tau and the e to the 1 tau combine to give us e to the 3 tau. When you multiply two exponential functions with the same basis, you add the exponents, and now it's a piece of cake. The integral of e to the 3 tau with respect to tau is 1/3 e to the 3 tau. This is as tau varies from 0 to t. We're almost there. This is e to the minus t times 1/3. Substitute upper limit of integration, e to the 3t. Substitute lower limit of integration, e to the 0 is 1. And maybe, I don't know, factor out the 1/3. Keep the 1/3 factored out, but put the e to the minus t into the parentheses distributed inside. So this becomes e to the 2t minus e to the minus t. Okay. Now, before we move on, I want to compare that with what we would have gotten the traditional way. So the traditional method, let's do this in Greek. Traditional method, let's put it in quotes because it's not really called traditional anywhere. The way we've done it in the past is we took 1 over s minus 2 times s plus 1, and we computed the partial fractions decomposition, which I won't show the work, I'll just put the partial fractions down. The partial fractions would be 1/3 over s minus 2 minus 1/3 over s plus 1. So the inverse Laplace transform, of our function would be the the inverse Laplace transform of 1/3 e to the, I'm sorry, the inverse Laplace transform of 1/3 over e to the minus s2 would be 1/3 e to the 2t minus 1/3 times the inverse Laplace transform of 1 over s plus 1 e to the minus t. Done. It's the same thing. It's the same thing. Now you might think, partial fractions is easier than the convolution. Yeah, for this problem it is. It might be. Partial fractions are pretty quick on this. But the convolution reaches more problems, or allows us to reach out to and solve different problems where partial fractions may not even be involved in the problem. Okay. Well, let's apply this convolution theory to the reason why we're here. The reason why we're here is not just to learn about Laplace transforms and convolutions and such. The reason we're here is to solve differential equations, ordinary differential equations, and boundary value initial value problems. So I'm going to solve another problem. This problem is going to be involve an initial value problem, and I'm going to write out a few things that we're going to need from calculus and from our course and from our course. Okay, so we're going to need this stuff. The first thing we're going to need is not a dot, but we're going to need the integral of e to the ax sine bx, which can be done by integration by parts. We'll just use a formula. So the formula for this is that it's a sine bx, the standard formula, minus b cosine bx times the quantity times e to the ax, and this is all over a squared plus b squared plus a constant in h. Okay. The second thing we're going to need, or at least we should be ready to use, are the shifting theorems. If you recall, the first shifting theorem says that the Laplace transform of e to the at f of t results in a shift to the right of the Laplace transform. So multiplying by e to the at in the t domain amounts to a shift to the right in the s domain. You mathematicians will hear this statement when you go further with differential equations. So multiplying by e to the at in the t domain results in a shift to the right in the s domain. The second shifting theorem says the Laplace transform of u sub a of t times a shifted function f of t minus a. So really, in the t domain, it's just the function f of t shifted to the right by a. Of course, the unit step function shuts off the function before a, so it's y equals 0 until we hit a, but then when we hit a, it's the shifted function a to the right. So the second shifting theorem says that the result is e to the minus as times the unshifted Laplace transform. Okay, so once again, the first shifting theorem says multiplication by e to the at in the time domain results in shifting to the right by a in the s domain, and kind of the reverse happens. If you shift to the right in the t domain by the second shifting theorem, it results in a multiplication by e to the minus as in the s domain. That's kind of interesting. In fact, it's very interesting from a strictly mathematical point of view. Okay, so we're going to need those things. We'll return to them as we need them. The example is to solve a first order differential equation, or an initial value problem involving a first order differential equation. So y prime plus y equals sine of t, with the solution going through the origin, y of 0 equals 0. And And I want to use, somewhere along the line, I want to use convolutions to do this. So let's proceed as usual. Let's take the Laplace transform of both sides. So we're going to have Laplace transform of y prime plus Laplace transform of y equals Laplace transform of sine t. Laplace transform of y prime is s times the Laplace transform of y minus y of 0, our formula, plus the Laplace transform of y. Laplace transform of sine of t, you've probably got that memorized by now. We've seen it so often. It's 1 over x squared plus 1. So far the usual stuff is going on. The y of 0 is 0, so we substitute that in. Also then factor out the Laplace transform of our solution on the left-hand side times s plus 1 equals that same 1 over s squared minus x squared plus 1. Divide both sides by s plus 1, and we get the Laplace transform of our solution is 1 over s plus 1, 1 over the quantity s plus 1 times s squared plus 1. Okay, this is not a new situation for us. If we wanted to do what we did in the past to find the solution, we would take the inverse Laplace transform and then use partial fractions on the right-hand side. So we're going to use convolutions now. The solution is the inverse Laplace transform, of course, of the Laplace transform. It's the inverse Laplace transform of our Laplace transform. But that Laplace transform can be written as the product of two functions of s, normal product, no convolution here. First semester or second semester algebra. Now the inverse Laplace transform of the product, though, by the convolution theorem says that this is the inverse Laplace transform of the first function convolved with, or star, or convoluted with, if you want to use that language, the inverse Laplace transform of 1 over s squared plus 1. So let's keep moving with this. I'm going to shift downward a little bit, no pun intended here. I'm going to come down a little bit, over to the left a little bit. The inverse Laplace transform of 1 over s plus 1 is e to the minus t star, or convolved with. The inverse Laplace transform of 1 over s squared plus 1 is sine of t. Okay. So let's keep going with this. Let's perform this convolution. This is where the question, should we have used partial fractions, would probably come in, because the actual convolution could be involved integral. So the convolution of e to the minus t with sine of t is the integral from 0 to t f of tau, e to the minus tau, times regular multiplication, sine of t, g of t minus tau, sine of t minus tau, d tau. And this is where you might actually ask that question, should I have actually gone back and done partial fractions instead? Because now we have to integrate this, and this is a standard integration by parts. I'm going to do this integration by parts, and I think I'll switch to variable blue for that, off to the left here. But I'm going to use tabular integration. Tabular integration, d. For those of you who are not familiar with tabular integration, you could use the regular form of integration by parts, but you're going to have to use a couple of iterations of integration by parts. So I think tabular integration is the way to go here. Okay. So the d is where we place our u, and the I is we replace our dv, the column, without the differential. So u is sine of t minus tau and dv, the I, what goes in the I column, is what's left. E to the minus if you're wondering how I got that, I used a device that I teach in Calc 2 called Liate device. The Liate device, very, very briefly, allows us kind of a systematic way and a rule of thumb for selecting u. And what you do in your integral is you go through the word Liate, the letters in the word Liate, one by one. You ask yourself first, are there any log functions? Nope, there are no log functions. Are there any inverse trig functions? Nope. Are there any algebraic functions, which means powers? Nope. Are there any trig functions? Yes. Yes. We have sine of t minus tau. Then we would finally search for exponential functions, but there were trig functions. So dv would be what's left, which would be e to the minus tau. So the next step is to in the u column to differentiate. So you find the derivative. Now, careful with the variable with respect to which you differentiate. The variable of integration is tau, so that's what we're differentiating with respect to. The derivative of sine of t minus tau with respect to tau is cosine of t minus tau. Chain rule gives us an extra negative, though, because the derivative of negative tau is -1. The derivative of cosine would be negative sine, but there's a negative there already in negative cosine. So the derivative of cosine would be sine of t minus tau. The chain rule, though, says we have to take derivative of the inside. The derivative of negative tau again with respect to tau is -1. Then we stop there because we notice that we have a repetition of the original u. So that's our signal with tabular integration of when to stop the process for this kind of integral. On the I column, we integrate the function e to the minus tau until we get to where we stopped with the D column. So the integral of e to the minus tau is minus e to the minus tau. The integral of that is another minus e to the minus tau, but there's a negative there to begin with, so we have our e to the minus tau back again. In the method also, though, in the tabular integration method, we insert outside in the first column a little plus, a minus, and a plus. We alternate plus, minus, and plus, and then we draw little arrows on the diagonal. And when we get to the last row, we draw an arrow back. Okay. Again, if you're not familiar with this, you could use, and I welcome you to, integration by parts, but you'll have to do it twice. The tabular integration really rules here. It really simplifies our work. I want to. Let's see, what am I doing here? I want to square off this work so it doesn't get in the way of our integral. Okay, so let's proceed. Our integral then equals, now referring to the tabular integration chart, plus from the red plus, sine of t minus tau times along the diagonal minus e to the minus tau. So we get minus e to the minus tau sine of t minus tau. Then we jump down one diagonal, red minus, black minus from the cosine, times e to the minus tau, so plus, net result, e to the minus tau cosine t minus tau. All of that is carried between tau equaling 0 and tau equaling t, and then the horizontal arrow indicates that we multiply in that direction and then also integrate in that direction. So we have minus from the net result of a red plus and a black minus the integral from 0 to t of e to the minus tau times the sine of t minus tau d tau. Okay? So very, very, very carefully, we're going to evaluate the first two terms that have been integrated. So substituting tau equals t into minus e to the minus tau sine t minus tau, substituting tau equals t, we get 0 from the sine of t minus tau term. We put tau equals, whoops, sorry. I apologize for my dog. He, that's got to be unnerving, especially if you're sitting quietly at home with maybe some music playing in the background, and they hear that almost wolf-like barking, so I apologize. Okay, so if we substitute tau equals t, the sine turns to 0. The cosine, on the other hand, the cosine, let's see, the cosine term, tau equals t, cosine of 0 is 1, so we have plus e to the minus t, that's it from the upper limit. Now the lower limit we subtract, tau equals 0. If tau equals 0, the sine term is going to give us sine of t. The exponential factor, e to the 0 is 1, but we're subtracting that, so plus sine of t. Now from the cosine factor at tau equals 0, we get e to the 0 is 1, and a minus cosine of t, because we're subtracting the value of the antiderivative at the lower limit, and then minus that original integral, that whole integral, 0 to t e to the minus tau sine of t minus tau d tau. And I think some people are going to see the mistake I made in the line above with that integral I wrote dt. So I'll fix it. The integral just right above that little t should be a tau. Okay. Now, we still have that integral on the right. There's a little bit of a trick we're going to use here from Calc 2. We can't lose sight of the fact that on the left-hand side we have 0 to t e to the minus, we're integrating 0 to t e to the minus tau sine of t minus tau d tau. So check out this line. The integral on the left, far left, is the same thing as the integral on the far right. If I add the integral on the far right to both sides, I'll have 2 of those integrals on the left. So 2 times the integral from 0 to t e to the minus tau sine of t minus tau d tau equals only the stuff that's left without an integral, the e to the minus t, the sine of t, cosine of t. So finally, and here's that little trick from Calc 2. Divide both sides by 2. If we divide both sides by 2, we get the integral we're looking for. The integral from 0 to t e to the minus tau sine of t minus tau d tau equals 1/2 e to the minus t plus, let me clean it up a little bit, e to the minus t plus sine of t minus cosine of t. And that's the result we were looking for. We get lost in all the algebra and calculus here. We were looking for the inverse Laplace transform of our Laplace transform for our solution, and that's it. The solution to the initial value problem was is indicated by the inverse Laplace transform, which is what we just found. Okay, so that's how we use this convolution theorem to find solutions to initial value problems. Again, we're only replacing one method with a new method. However, the new method being the convolution integrals. However, this convolution theory goes way beyond just being a second choice for taking inverse Laplace transforms. Second choice to avoid partial fractions. Let's take a look at a use of the convolution theorem to solve a very important physical problem that can't be done really with partial fractions alone. Okay. In the early 1900s, a mathematical biologist by the name of Volterra introduced into the mathematics community a type of equation that's similar to a differential equation. Remember, a differential equation is any equation that has one or more derivatives of a function, unknown function in it. Well, there are also equations called integral equations, and they occur really often in the sciences. One, and it's a real popular one because it's kind of simple to solve. Integral equations, like differential equations, can be extremely difficult to solve. Let's take a look at something called the Volterra integral equation from mathematical biology. Okay, and the general form, or a general form of this equation looks like this. It looks like y of t, that's the unknown function, equals h of t. That's sort of a forcing function. So this h of t is known, plus, and here's where it gets interesting, the integral from 0 to t of some additional function which is known, w of t minus tau, times that same solution function, the function we're trying to find, y of tau, t tau. This strange looking little equation, especially if you've never seen it before and you've only studied differential equations. There's no derivatives in this. This is called an integral equation, where the unknown function y of t is contained on the left-hand side, and an integral involving the unknown function is on the right-hand side. Okay, and now look at the Volterra integral equation a little more carefully. This can be written as y of t equals that known h of t plus this is a convolution of w of t and y of t. So the Volterra integral equation can be written in convolution form as y of t equals h of t plus the convolution of the unknown w of t and the unknown y of t. Okay, it looks like an algebraic equation. We want to solve for small y of t. You would think maybe just subtract the w of t convolved with y of t from both sides and somehow isolate y of t, but that's not really quite that easy because it's not a regular multiplication we're looking at on the right-hand side. In any case, let's solve a specific example. Let's solve a specific example. So for example, here, solve the equation y of t equals constant 4 for h of t minus the integral from 0 to t of cosine of t minus tau times y of tau. So this is a Volterra, an example of a Volterra integral equation. Okay. Well, it would be nice to get rid of that integral, but we can't because we don't know what y of tau is. So we're stuck with that there. That's what makes it an integral equation. I'm going to rewrite this equation though in convolution form. So this is y equals 4 minus the convolution of y of t. Actually, I'm going to do it that way. Convolution of cosine of t and y of tau t. Okay. Now we haven't proved it, but the convolution, in fact, turns out to be a commutative property, convolution product. So we can write this as y of t convolved with cosine of t. Okay. Now I'm going to take the Laplace transform of both sides. So let's apply the Laplace transform of both sides. So Laplace transform of y of t then equals, Laplace transform of 4 is 4 over s minus the Laplace transform of that convolution, y of t convolved with cosine of t. But we have a formula for the Laplace transform of the convolution product of two functions of t. And that was the big result. The convolution, the Laplace transform of the convolution product is the regular product of the individual Laplace transforms. The dot here is regular dot. The Laplace transform of y of t times the Laplace transform of cosine of t. Okay. Notice what happened in the transition from the t domain to the s domain. By taking a Laplace transform, we eliminated the convolution from the Volterra equation. This is just a regular product. So I'm going to get rid of the of t's. I'm just going to write Laplace transform of y, just for to simplify things a little bit, simplify the notation, equals 4 over s minus the Laplace transform of y. And we know the Laplace transform of cosine of t is s over s squared plus 1. From here, we just do what we've been doing over and over again when we solved differential equations using Laplace transform. We isolate the Laplace transform. So I'm gonna get the Laplace transforms on one side, and I'm gonna factor them out. So on the right-hand side, I'm going to have Laplace transform, so Laplace transform times 1. If I bring over the other term with the Laplace transform, I'll have plus s over s squared plus 1 on the left-hand side, and simply 4 over s on the right-hand side. So if you didn't look above, it would look like the same stuff we've been doing all along. If you didn't look at the fact that this came from a new kind of equation, not a differential equation, but an integral equation, this looks like the same old stuff. Okay, so I'm combining the two terms in the brackets on the left. I'm going to isolate the Laplace transform of our solution over. Actually, it's not just going to be 4. It's going to be 4 times s squared plus 1 over s squared plus s plus 1. Okay. So, well, we would like then the inverse Laplace transform of this result. So we're going to use some partial fractions here. Let's use some partial fractions on this. So I'm going to leave out the partial fractions work, which, as you very, very well know, can take like 10 to 15 or 20 minutes to do. So the partial fractions decomposition on this turns out to be 4 over s minus 4 over s squared plus s plus 1. And I'll write out here, I already said it. So partial fraction work do on a test. Although I probably would allow it if you used an online partial fractions program, if you just cited that, if this were a take-home test, which for this semester, spring to 2020, pretty much is. So here's our partial fractions decomposition. So the elephant in the room is that next term. I need the inverse Laplace transform of that 4 over s squared plus s plus 1. There's a little work to do with that. I'm gonna show you the work. So this is 4 over s. I'm gonna come over to the left a little bit. I think I might need a little more room. I'm going to I'm going to complete the square in the denominator. So the denominator is s squared plus s. The coefficient of s is 1. To complete the square, we take 1/2 of that, which is 1/2, square it, and add it, and subtract it. Okay, I guess I could do all the completing the square stuff behind the scenes too, but if I only do stuff behind the scenes, there'll be nothing left on the video. So s squared plus s plus 1/4 factors into s plus 1/2 quantity squared, then plus the 3/4. And this looks like a shifted Laplace transform. If we didn't have that plus 1/2, it would be s squared plus 3/4 with a constant in the numerator. The inverse Laplace transform looks like a sine, but it is shifted. It is a shifted Laplace transform. So we're going to need the first shifting theorem. The first shifting theorem, and I'll write it off in the right here, just to remind us. The first shifting theorem, written in reverse, says the inverse Laplace transform of the shifted Laplace transform. The inverse Laplace transform of f of s minus a is e to the at times the inverse Laplace transform of the unshifted Laplace transform. Or it's a more elaborate way of saying e to the at times small f of t. Okay, so we'll use the first shifting theorem here. I'm going to manipulate this Laplace transform, though, a little more algebraically to make things work out. So this is 4 over s minus, in fact, that 4 in the numerator, I'm going to factor out, which really leaves 1 in the numerator. I'm not going to put 1 there. Notice in the denominator we have s plus 1/2 squared plus 3/4, which is like having s plus radical 3 over 2 squared. I'm trying to build up the Laplace transform to look like a common Laplace transform for the sine that we were talking about. Remember, the Laplace transform for the sine, Laplace transform of the sine of bt is b over s squared plus b squared. So the b is radical 3 over 2 in our problem. So I need a radical 3 over 2 on top. I'm just going to put it up there. Can't do that. That changes the value of stuff. So I'm going to multiply by 2 over radical 3 to balance it. Okay. I'll clean this up a little bit before I start using the shifting theorem. This is 4 over s. I'm going to combine that 4 with the 2 over radical 3 to give us 8 over radical 3. So 4 over s minus 8 over radical 3 times that same old radical 3 over 2 s plus 1/2 squared plus 3/4, or radical 3 over 2 squared. Now we're going to use the first shifting theorem. So y of t is the inverse Laplace transform of this Laplace transform, this function of s. The inverse Laplace transform of 4 over s, well, the inverse Laplace transform of 1 over s was 1. the inverse Laplace transform of 4 over s is 4 times 1 or 4. Minus 8 over radical 3 times the inverse Laplace transform of this shifted to the left by 1/2, shifted to the left by 1/2 Laplace transform. And you probably caught an exponent that's a little big in the denominator there. I'll get it where I start seeing it in comments below. There we are. So the Laplace transform of f of s minus a is e to the a t. Well, a is negative 1/2, so e to the minus 1/2 t times the inverse Laplace transform of the unshifted radical Laplace transform radical 3 over 2 s squared plus 3/4, and it's essentially over, my good students. This is 4 minus 8 over radical 3 e to the minus 1/2 t. This is in the perfect form for us to identify the sign of radical 3 over 2t, and that is the solution to this Volterra integral equation. Okay, so that also completes section 7.4. I'm going to continue in this video segment with section 7.5. If you'd like a break, I would not blame you. If you've been in for the long haul of this video segment, it's been quite a stretch. So I recommend a break. If you're not into a break, just continue to listen, and we'll continue with section 7.4. I mean 7.5. Okay, so with the magic of my Surface Pro, I'm able to instantly write our first example, our only example from section 7.5. 7.5 again has to do with systems of linear differential equations. We'll get to exactly what that means. You probably know exactly what that means. Systems of equations mean multiple equations. Differential equations, you know what they are. In any case, systems of linear differential equations and using Laplace transforms to solve them. So consider two tanks, each with a volume of 100 gallons connected together by two pipes. So I'll stop there for a second. Right below I drew those two tanks. The tanks are tank 1, T1, and tank 2, T2. And they're connected with two pipes that allow liquid to be exchanged between them. So if you haven't guessed, this is a mixture problem, but we have two tanks instead of one tank. I think in chapter 3 we had 3.6, I think it was, we had one tank. Okay, the first tank, T1, initially contains a well-mixed solution of 5 pounds of salt in 50 gallons of water. So right by tank 1, I'm going to write at t equals 0, we have 5 pounds of salt in 50 gallons of water mixed together. Okay, all right. The second tank, T2, initially contains 100 gallons of salt-free water. So in tank 2, we have also at t equals 0, we have no salt in that tank. We have 0 pounds of salt, but we have it in, I think I've already forgot what I wrote. Oh, 100 gallons of water. So 100 gallons of water. Okay, so this is what's happening initially. Okay, so continuing with the green sentence, or that begins in green. A pipe from tank 1 to tank 2 allows the solution from tank 1 to move into tank 2, to enter tank 2 at a rate of 5 gallons per minute. Okay, so we have the lower pipe, if you will, allowing water to go from tank 1 to tank 2 at 5 gallons per minute. A second pipe from tank 2, the upper pipe, allows the solution from tank 2 to enter at the same rate, 5 gallons per minute. So we have an interchange of liquid between these two tanks at the same rate. So one thing is staying constant in each tank through time, and that's volume. The volume in each tank is not changing, because as 5 gallons per minute are leaving one tank, 5 gallons and entering the second tank, that same rate, 5 gallons per minute of liquid are exchanged between the other tanks. I don't think that sentence turned out real well. So the volume remains constant. Okay. Assume that the salt mixture in each tank is well stirred. So as all this is happening, we're sort of shaking the tank so that everything stays mixed real nicely as time goes on. The question is, or the problem is, to find the amount of salt in each tank as a function of time. Okay, and I think you're gonna find this problem not as complicated as it really looks to begin with, especially if you're okay with the mixture problems we did before. I think the setup here is actually simpler than some of the work you've done before. Okay, we want the amount of salt, pounds of salt, in each tank as a function of time. So let's identify some variables. I'm gonna let A1 for amount in the first tank, A1 of t equal the amount of salt in tank 1 at time t. So let this equal the amount of salt in tank 1, T1, at time t. Let A2 of t equal the amount of salt in tank T2 at time t. The tongue twister. The amount of salt in tank 2 at time t. So let's see if we can figure out differential equations, two of them, differential equations satisfied by A1 and A2. Let's compute the rate of change of the amount of salt in tank 1. That would be dA1 over dt. So the rate at which of the amount of salt in tank 1 is changing is just as before. The rate salt enters tank 1 minus the rate salt leaves tank 1. Leaves tank 1. Okay. Now here's where it gets a little complicated. We need to actually compute these two rates. Okay. Well, the rate that salt enters T1 is the concentration of the salt entering, times the rate that the salt is entering. You'll understand this as soon as I write this out symbolically. It's the concentration of the salt entering. Well, from where is the salt entering tank 1? It's entering from tank 2. So the concentration of the salt in tank 2 is A2 pounds divided by the volume in A2. In A2, the volume is a constant 100 gallons. That's the concentration of the salt in tank 2 at time t. And that's entering at a rate of 5 gallons per minute. Now look what happens to the units. The gallons cancel, and you're going to end up with pounds per minute. And that's exactly what the units of the rate of change of salt should be. That's the rate at which salt enters. So now subtract the rate at which salt leaves tank 1. So the rate at which salt leaves tank 1 is the concentration in tank 1, which is A1 pounds divided by the volume in A1. Well, A1 is got a constant volume of 50 gallons. It's always got 50 gallons. That multiplied by the rate at which liquid leaves T1, and that's 5 gallons per minute. Okay. Let's do the same thing for the rate at which the rate of change of the amount of salt in tank 2. Okay, that should be the rate that salt enters T2 minus the rate salt leaves T2. Okay, so how fast, back to our drawing, how fast is salt leaving the second tank? Well, we know how fast the liquid's leaving. It's 5 gallons per minute. But how fast is the salt, entering? Oh, I said that backwards. How fast is the salt entering T2? It's entering T2 from T1 at 5 gallons per minute. But how fast is the actual salt itself entering T2? Well, it's entering from T1. In T1, the concentration is again A1 pounds for, entering, A1 has 50 gallons, 50 gallons. And the rate at which the volume is entering T2 is 5 gallons per minute. So again, the rate at which salt enters T2 from T1 is the pounds of salt in T1, A1, divided by the volume of T1, which is always 50, times the rate at which liquid enters T2. So, and finally, the rate of salt, subtracting the rate at which salt leaves T2. Well, the concentration in tank 2 is A2 pounds, and there's always 100 gallons in A2, times the rate of 5 gallons per minute. All right. Okay, so let's see what these two differential equations simplify to. If we get rid of all the units, we're looking at, I'm going to use A1 prime for dA1 dt. We get A1 prime equals 1/20th, my goodness, 1/20th A2, because 5 goes into 120 times. I'm simplifying the first differential equation, minus 5 goes into 50 10 times, 1/10th A1. Okay, A2 prime equals then, concentrating on the second differential equation, 5 goes into 50 10 times, so 1/10 A1 minus 5 goes into 120 times, 1/20th A2. Okay, and so this is a system of differential equations. These are the two differential equations that are satisfied by the amounts of salt in each tank. This is called a system of differential equations. Okay. Well, we can't use any of the methods we used for solving systems yet, because we don't know what the functions are. We have differential equations satisfied by the by the A1 and the A2. So now, if you haven't guessed, we're going to use Laplace transforms to solve this system. We're going to take the Laplace transform of each of the differential equations. Okay, well, we're going to need some initial conditions. So we're going to go back to the drawing. Look by T1. Initially, I have 5 pounds of salt dissolved in 50 gallons of water. So A1 of 0 is 5. And for T2, notice I had pure water initially. So the initial amount of salt in the tank, A2, at T equals 0, so A2 of 0 is 0. So there are our initial conditions. Now let's use some Laplace transforms. Let's take the Laplace transform of each of these differential equations. Okay, so concentrate on the first one. I want the Laplace transform of A1 prime. That should equal 1/20th Laplace transform of A2 minus 1/10 times the Laplace transform of A1. The Laplace transform of the second differential equation. On the left-hand side, Laplace transform of A2 prime equals Laplace transform on the right-hand side, 1/10 times the Laplace transform of A1 minus 1/20th times the Laplace transform of A2. Okay, so let's continue on back to the Laplace transform of A1 prime. I'm going to use the formula that we've been using over and over again, but for a different kind of variable than y. The formula I'm using is off to the right here. Laplace transform of y prime equals s times the Laplace transform of y minus y sub y of 0. So I'm going to use that formula, but applied to the variables A1 prime and A2 prime. So to our first differential equation, we get s times the Laplace transform of A1 minus A1 of 0 equals the right-hand side, 1/20th times the Laplace transform of A2 minus 1/10 times the Laplace transform of A1. Now to the second differential equation, Laplace transform of A2 prime should be s times the Laplace transform of A2 minus A2 of 0, and that equals the other side, 1/10 Laplace transform A1 minus 1/20th times the Laplace transform of A2. Now from here I'm going to make a kind of a big algebraic leap. And if I go too quickly, pause the video, and if necessary, go back a few seconds if you miss some stuff. But I have now 2 equations that need to be solved. And what I'm looking for is, for the variables involved are actually the Laplace transform of A1 and the Laplace transform of A2. So the first thing, I'm going to apply my initial conditions, namely A1 of 0 is 5 and A2 of 0 is 0. So into this system, I'm going to be putting A1 of 0 is 5 and A2 of 0 is 0. Now I'm going to make, like I said, I'm going to make a pretty big algebraic leap here. I'm going to get the 5 and the 0, the constants, to the right-hand side, and everything else on the left. And I'm going to factor out common factors and so forth. So when I do that, I'm going to get s, and the Laplace transform of A1 from the right-hand side in the first equation comes over, so I'm going to have s plus 1/10 times the Laplace transform of A1. Alrighty, so minus 1/20th times the Laplace transform of A2, and that should equal 5. I'm going to do a similar thing with the second equation. I'm going to isolate the A1, Laplace A1 and Laplace A2 on the left-hand side. So I'm going to get minus 1/10 as a coefficient of the Laplace transform of A1. Oops, let me clean that parentheses up. A1. And then, let's see here. Oh, I got lost for a second. Plus S plus 1/20 times the Laplace transform of A2. And that equals 0. So this is my system of equations. With the variables in this system are Laplace A1 and Laplace A2. At this point, we can start using we can decide on what method we want to use. We can go Gaussian elimination, Gauss-Jordan, inverses, since it's a square system, or Kramer's rule. The last one, Kramer's rule, tends to be a little easier on the eyes for us here. We're not capable of substituting or using Gaussian or Gauss-Jordan elimination methods here too efficiently, because our coefficients are not constant here. So I'm going to use Kramer's rule. So I'll indicate that here. So Kramer's rule used here. Okay, Kramer's rule involves 3 determinants. I'm not going to call them use the variable a, because we're using the variable a for amount. I'm going to call them d for the determinant of the coefficients, d1, and d2 for the other 2 determinants. So d, the determinant of the coefficients, is, well, the coefficient of the coefficients of Laplace A1, the first equation, the coefficient is s plus 1/10. Yes, I realize my s's still look like 5s. And then in the second entry is negative 1/20, then negative 1/10, and s plus 1/20, that determinant. Okay, I'm going to compute that determinant. That determinant is s plus 1/10 times s plus 1/20. And that's minus 1/10 times 1/20. Okay. Now, when all the dust settles on this, when I FOIL out the first 2 terms there and subtract 1/10 times 1/20, I'm going to get s squared plus 3/20 s. Okay, so that's my d in Kramer's rule. That's the determinant of the coefficients. d1 we get by replacing the first column with the coefficients. So that's 5 and 0. First column in d with the coefficients in the system, 5 and 0. And then negative 1/20 and s plus 1/20. And that's a real simple determinant. If I compute this determinant, I'm going to get 5 times s plus 1/20, which is 5s plus 1/4. Okay, finally, in terms of determinants, d2, we get by leaving the first column in d alone and replace the second column this time with the constants in the system. And this one is even simpler determinant. So we're going to get minus 5 times negative 1/10, or 5/10, or 1/2. Okay, so now let's continue with Kramer's rule. So the variables again are Laplace A1 and Laplace A2. So Laplace A1 is d1 over d, which is 5s plus 1/4. There's some irony there. My s's look like 5s, and now I need 5 times s. So I'll try to be real clear. Here's 5, and here's s. It still looks like 55. So 5s plus 1/4 either looks like 55 or SS over D, which is S squared plus 3/20th S. Okay. If you simplify that, well, if you factor the denominator, you get 5S plus 1/4 over S times S plus 3/20th. And that is really screaming out at us for partial fractions. Okay, so I'm going to save the partial fractions until after I've gotten the Laplace for A2, and we'll do that all at once, partial fractions all at once. So the Laplace for A2, again by Kramer's, is D2 over D, Kramer's rule. Same S squared plus 3/20th S. Same factorization, S times S plus 3/20th, but the simpler D2 of just 1/2. Okay. Now, by some behind-the-scenes magic, I'm going to do the partial fractions. I'm going to write out what the partial fractions look like. So Laplace A1, after we do partial fractions, is 5/3 over S. And let's see what else is. Oh yeah, excuse me. Plus 10/3 over S plus 3/20th. And for the Laplace transform of the amount of salt in the second tank, A2, that turns out to be 10/3 over S minus 10/3 over S plus 20. S plus 3 over 20. Over 20. Okay, and you can, if you're so inclined, you can verify the partial fractions. You don't really have to. I think, in fact, I know that I'm going to assign a homework problem that's almost the same thing, so you'll be doing some partial fractions. So now let's take inverse Laplace transforms. This is the simple part. Finally, something simple. So A1 is equal to 5/3 times the inverse Laplace transform of 1, which is, I'm sorry, 1 over S, which is 1, so it's just 5/3, plus 10/3 times the inverse Laplace transform of 1 over S plus 3 over 20, which is E to the minus 3 over 20t. Such a nice, simple inverse Laplace transform here. And the second one also, 10/3. Inverse Laplace transform of 10/3 over S is 10/3 minus 10/3 times E to the minus 3 over 20t. Okay. So in terms of the solution to the problem that's done, I want to do a final kind of analysis on this. This is a physical problem. Most of you are science majors, so to have just a solution is cold, and if you're not a math major, it's cold and kind of like, okay, now what? So I want to notice what happens with the amount of salt in each tank as t approaches infinity. So as time goes on, we got these tanks interchanging liquid between the two tanks at the same rate. What happens to the amounts in tank 1 and in tank 2 of salt? Notice as time goes on, so as t approaches infinity, A1 approaches 5/3 pounds, and A2 approaches 10/3 pounds of salt in the tank. I'd like to address the question, does this make sense? Does this make sense? Well, The answer is yes. Yes, because we found a solution that makes it happen, so just because of that it makes sense. But let's think about this. Let's think about this. Tank 1 started with 50 gallons, and throughout all time is going to have 50 gallons. It's never going to change. And similarly, Tank 2 will always have 100 gallons in it. The concentrations in each tank are constantly changing. But each tank will, since we're interchanging, the rates of interchange of liquid are exactly the same. For 5 gallons leaving one, 5 gallons per minute leaving the other. So tank 1 will always have 50 gallons in it. Now, how many gallons are in both tanks combined? Well, the first tank's going to have 50, the second tank's going to have 100, so 150. So the fraction of the volume, the total volume of 150 in tank 1 is going to be 150 gallons in tank 1 over 150 gallons total. So tank 1 will always have 1/3 of the total volume of water, of mixture. Always has 1/3. 50 is 1/3 of 150. On the other hand, tank 2 will always have 100 gallons in it. And there will always be a total of 150 gallons in both tanks. And 100 over 150 is 2/3. No big surprise. So tank 1 is always going to have 1/3 of the mixture in it. The concentration is always changing in each tank. Total of the total volume. The concentration of salt is changing in each tank continuously. So it seems reasonable that with this constant mixing of the solutions, the constant mixing of solutions, and the constant changing of the amounts of salt in each tank, that the amount of salt, it seems reasonable. It seems reasonable that the amount of salt in tank 1, that the amount of salt in T1 should approach well, it's always going to have 1/3 of the total volume. So it seems reasonable that the amount of salt in tank 1 should approach 1/3 of the total amount of salt available in the system. 1/3 of, and there's only 5 pounds of salt total swishing around. Okay, so eventually the amount of salt in tank 1 should approach 1/3 of that 5 pounds, or 5/3 pounds. Similarly, in tank 2, also, it seems reasonable. Sorry, I'm dragging this out a little bit. Reasonable. That the amount of salt in tank 2 should approach, there's always going to be 2/3 of the total volume of liquid available in T2. So it seems reasonable that as we swish all this liquid around back and forth, that the amount of salt in the second tank should approach 2 times the total amount of salt available in the system. And that's 10/3. So these quantities, these last 2 quantities of 5/3 of a pound of salt in tank 1 and 10/3 of a pound of salt in tank 2 seem reasonable just from a logical standpoint, and that's exactly what we predicted. That's exactly what we predicted in my initial statement of what to notice. Okay, so this takes us to the end of section 7.5. In the homework in section 7.5, I'm going to be posting that very quickly, very soon. I'm going to assign an application problem that is very, very similar to this. I may or may not assign 1 or 2 or a couple problems where you just solve systems that have no physical background, and you solve those systems exactly the same way. Apply Laplace transforms. You use Kramer's rule to simplify the Laplace transforms, and then take inverse Laplace transforms. In any case, that's all for the moment, and I'm looking forward to talking with you again soon.